Imagine for just a moment a world where absolutely everything has come to a complete stop. Every single thing without exception. Not even the tiniest twitch, not even a single atom moving in the slightest. And no, this isn't some poetic metaphor or a scene out of a sci-fi movie. This is about a very real boundary in physics, a theoretical temperature called absolute zero. Absolute zero marks the bottom of the temperature scale, a point where all thermal motion in matter is expected to come to a full and total halt. And here's where things get really interesting. If all matter stops moving, does that mean time itself also stops flowing? As if time too just drifts off into a deep sleep. Even if you're already frozen in anticipation for what comes next, gather your strength and hit that subscribe button. And do us a favor, warm up YouTube's processor a little by sharing this video around. Hey there everyone! We tend to assume that time is always moving forward, no matter what. It feels like a constant backdrop to our lives, a stage where all our experiences play out. But what if we removed every bit of movement from the picture? Would time itself vanish too? If everything else in existence just stopped, what would happen to time? Welcome to our channel. Let's explore that question together. What is absolute zero? Let's start by clearing up something we've all probably heard about back in school. What exactly is absolute zero? It's not just a way of saying something is really cold. Absolute zero is the lowest possible point on the temperature scale, equal to minus 459.67 degrees Fahrenheit, or zero on the Kelvin scale. According to classical thermodynamics, at this temperature, all thermal motion of particles comes to a stop. That means no random movement inside the material, no vibrations, and no collisions between molecules. But here's a key point. Stopping doesn't mean those motions disappear completely. Because at the microscopic level, it's not classical physics calling the shots, it's quantum physics. And quantum laws often clash with the everyday way we think about matter and motion. Even when a system gets incredibly close to absolute zero, particles still have to wiggle around just a little bit. This is known as zero-point motion. That's why matter never truly comes to a full stop. So why exactly is it said that reaching absolute zero is impossible? First, according to the third law of thermodynamics, reaching 0 Kelvin would require an infinite amount of energy. And that's physically impossible. Second, there's Heisenberg's uncertainty principle, which says you can't know a particle's position and momentum exactly at the same time. But if you assume something is perfectly still, that means you'd have to know both where it is and that its momentum is exactly zero. And that directly violates Heisenberg's principle. In other words, a state of complete stillness isn't just unachievable, it's not even theoretically possible. That's why absolute zero isn't something we can ever truly reach. It's an ideal limit we can get closer and closer to, but never actually touch. Time and atoms. To us, time feels like something separate from everything else, steady and unchanging. But in reality, we're not actually experiencing time itself. What we are really sensing is change. A pendulum swings back and forth, hearts beat in our chests, and day slowly turns into night. Electrons jump between different energy levels inside atoms. From sundials to atomic clocks, every timekeeping device we've ever built isn't measuring time itself, but rather tracking the regular motions of the universe, like Earth's orbit around the sun, the swing of a pendulum, or the jump of an electron from one energy level to another. Now, imagine just for a moment that every single one of those processes suddenly came to a stop. That's absolute zero. Particle motion grinds to a halt. Even atomic clocks, the most accurate instruments we've ever created, would stop ticking. Because at that point, there's nothing left inside them that could mark the passage of time anymore. Electrons would settle at the lowest energy level and stop jumping altogether. Every electron would be stuck in its ground state, unable to be excited to a higher one. So, does that mean time itself would vanish right along with motion? The answer's not quite that simple. As we mentioned earlier, even near absolute zero, motion never disappears entirely. Quantum fluctuations still continue, no matter how tiny they get. It's as if matter itself refuses to ever fully come to rest. And this brings us face to face with two big questions. First, is time something that exists on its own? Or is it just a way to measure change, a label for the gap between one event and the next? Second, if particles begin to move more slowly, does that mean time itself slows down with them? The search for answers to these questions takes us right to the edge of what we currently understand about the true nature of time. Quantum mechanics, motion without moving. When we hear the word stillness, we tend to picture something completely frozen, unmoving, and static. But in the world of quantum mechanics, that image falls apart. Even in cutting-edge experiments, including some conducted aboard the International Space Station, where matter is cooled to temperatures near absolute zero, motion never truly disappears. Instead, it takes on a different form. Rather than physical movement through space, it becomes a subtle fluctuation in probability. In other words, in the ultra-cold environment close to absolute zero, particles barely move at all, but their wave functions still shimmer and shift ever so slightly, as if they're gently breathing, never completely flat or still. We see proof of this in strange phenomena like superfluid helium. When helium is chilled near absolute zero, it loses all viscosity and can flow endlessly without friction or any loss of energy. That's because, at that point, the movement of helium atoms is no longer driven by heat, but by quantum fluctuations. The Casimir effect is another fascinating example. This is a phenomenon where two metal plates placed in a vacuum attract each other, not because of any outside force, but due to quantum fluctuations that cause virtual particles to appear in empty space. What we're seeing here is the trembling of the vacuum itself, a kind of quantum ripple in nothingness. So even if everything looks completely still, under the surface, something is always appearing, disappearing, and shimmering in and out. Things may seem motionless, but in reality, there's movement, and that's the paradox. And now, those two big questions we asked earlier come back to the surface. If change is still possible within a system, even if only at the level of probability, can we still say that time exists within it? And if those changes happen less and less often, does time itself slow down to reflect that decrease in activity? Maybe time isn't tied to the motion of objects through space the way we're used to thinking. Maybe, just maybe, it's linked to the very possibility of change. If something can still change, even while sitting perfectly still, then time hasn't stopped. It's still quietly flowing on. Time near absolute zero. We know that as you approach the speed of light, time begins to slow down. This isn't just a theory, it's a proven effect predicted by Einstein's theory of relativity. For an outside observer, time appears to move more slowly for any system that's moving at high speed. But for someone inside that fast-moving system, time feels completely normal. They don't feel time slowing down at all. In other words, the flow of time isn't absolute. It's relative, and it depends entirely on where you're observing from. The speed of light is a limit we can never reach, but the closer you get to it, the more time stretches out. So, what if absolute zero is like the temperature version of that limit? After all, both 0 Kelvin and the speed of light are unreachable boundaries according to the laws of physics. And as we approach either one, we observe something very similar: dramatic slowdown in processes. In ultra-cold environments, atomic processes begin to crawl. Measurements using optical atomic clocks show that when atoms are cooled to the extreme, the frequency of electron transitions drops. The ticking of time becomes faint, scattered, and slow. Even if time itself doesn't disappear as a physical concept, everything starts moving as if it's trapped inside frozen gel, sluggish and stretched out. So both extreme cold and high-speed motion have something in common. As we get closer to those limits, matter loses its ability to change rapidly, and along with that, we lose our normal sense of time flowing. But we need to understand that the slowing of time inside a cold system and the relativistic slowing of time are fundamentally different things. In the cold scenario, it's the physical activity that slows down. In the relativistic one, time itself, as a coordinate in the fabric of space-time, actually stretches. Put another way, in a near-zero environment, time moves as usual, but there's nothing in motion to show it. In relativistic motion, from an outside observer's perspective, the duration of time between events appears to lengthen. So even at 0 Kelvin, time doesn't vanish. But it does lose its operational meaning. Without any processes, there's nothing to measure and nothing to compare. Even if everything stops, the structure of time still lingers, as a possibility, as a background, as the ghost of future change. Maybe at this ultimate level, time and space are no longer two separate things. They may fuse into a single, seamless fabric, impossible to tell apart. And at the deepest quantum level, that fabric is what the entire universe is made of. So even if everything looks still on the surface, down below, the quantum foam is always bubbling. It's made of tiny ripples of geometry and energy, refusing to let existence ever fully shut down. Maybe the reason time never disappears is because it's inseparable from the very nature of space itself. No matter how cold things get, no matter how still matter becomes, the heartbeat of reality never stops. Absolute zero isn't the end of the universe. It's the universe in its ultimate moment of pause. And even in that pause, the breath of possibility still lingers, faint but alive. If everything else stops, does time stop too? Absolute zero marks a boundary, a limit we can approach but never actually cross. It's the extreme edge of temperature, where all the movement and activity we associate with life and motion seem to vanish. But that stillness is only how it appears. In truth, not everything has completely stopped. The fundamental forces don't shut down, and electrons don't fall into atomic nuclei. Space itself doesn't disappear. Quantum fluctuations, the subtle pause of reality, still remain, even if they exist on a level we can't detect. And that's exactly why, even if the entire world came to a halt, time itself wouldn't vanish. Time might slow to its absolute limit. Its rhythm might fade into unfamiliar patterns. But as long as there's even one flicker of change, one tiny vibration, one single interaction, time can't cease to exist. Maybe time doesn't flow at all. Maybe it simply is, like a field or a structure, only revealing itself when something stirs. In a perfectly frozen state, where nothing moves and nothing exists, what remains is possibility itself. The kind of possibility physicists describe as the fabric of space-time, or the bubbling of the quantum vacuum. Absolute zero doesn't erase time. But maybe it melts time and space together into something inseparable, a single unified presence. And with just the tiniest ripple, the smallest spark of energy, time starts ticking again, step by step, just like we remember. Tick-tock, tick-tock. If you enjoyed this video, give it a like and feel free to share it on social media. Thanks so much for watching. Until next time, see you again soon.